Morning. Yeah, is it long? I'll check 1, 2. Morning. Going up to the back there?
Did anyone leave a note behind?
Not that I'm aware of. Okay. Why don't we get started, guys? There might be a few people coming in yet. In your books, we're finishing up chapter 7, which is on aircraft systems. And I believe we're on, let's see, page 7-28, somewhere on here. Few more people coming in. A few more minutes here. Right. How you guys doing? Page 7-28. Let's see. So let's go to fuel system. I think so. Aircraft fuel is susceptible, to water contamination. And when you get water inside of fuel, it can freeze if it gets cold enough. One of the things they do sometimes will put in additives, like the jets out here, because they fly at such high altitudes, and they're often really cold air. They have to have certain additives to prevent the fuel from either gelling or freezing itself. So they'll some concoction or what it is that they put in there, but it's something that they actually into it freezing up. And they were obviously, with aviation, we're really concerned with any kind of ice forming on the wings, ice in the engine, things like that. System icing that's coming from the fuel icing different wings and freezing or icing and sticking to it. So they kind of they can in the fuel and aircraft to prevent itself there. Some of the fuel fired heaters. So what that's referring to is for like general aviation aircraft, typically, the single engine ones, you've got the engine out in front, right here, and right behind it is the pilot and co-pilot here. So what they do is they actually draw heat off the engine, off the exhaust manifold. There's like a can that actually exists around the exhaust manifold, and it collects heat and allows it to be conducted into the cabin. Now, what do we have to be worried about with exhaust gas? Anybody know? Yeah, that carbon monoxide. Or CO, yeah. So carbon monoxide is definitely, you can't smell it or anything like that. If it gets in the cockpit, it could be disastrous. So the shroud is inspected. It's called a shroud. Basically, it looks like a coffee can. It's around the exhaust manifold. So if there's any leaks in the exhaust itself, they could get into the shroud in the engine compartment itself. That could nuts. Sorry, guys, this is happening again. Let's see.
Joe, your microphone is turned off.
Okay, can you hear me now?
Yes.
Okay, very good. Thank you for pointing that out. I appreciate it, Olivia. Okay. Let's see. All right. Let's talk about aircraft pressurization systems. With aircraft pressurization, this is on 735. We pressurize aircraft cabins because, anybody know why we would have to pressurize an aircraft cabin? Yeah, do you know about what that level is? Yeah, it's around 13,000 feet, somewhere in that area. You really want to provide, actually, you have to provide about 15,000. You have to provide oxygen. And in that case, if you can pressurize the aircraft, that would solve that issue there. But pressurization systems, basically what they do is, first off, the aircraft cabin itself has to be, completely sealed up. Okay, so there can't be any leaks in it. That's one thing about a pressurized aircraft. And then second, you have to have some way of pressurizing or adding, air pressure into that system, because when you're flying at 20,000 feet, all of the air in the cabin wants to escape, right? So we have to seal it off. We have to put pressure into it because we've got less over. Do we have high pressure on the aircraft at 20,000 feet or lower pressure? Yeah, it'd be much lower, right? So when you have lower pressure at that altitude, obviously we need to pump, lots of pressure in here to make it feel in the aircraft like we're flying at maybe 8,000 or 10,000 feet, something like that. Most commercial airliners pressurize their cabins for around 8,000 to 10,000 feet. So when you do go on a pressurized aircraft, you're going to feel that. For general aviation aircraft, they may allow you to pressurize it up to as high as like 12,000 or something like that. But in like commercial airliners, they're all around that 8,000 to 10,000 feet there. So what happens, they've got just a couple of these, and I don't know if you're going to see much of this on the test, but I do want to go over it. Ambient air is the outside air pressure, that's, the pressure around the outside of the aircraft there. And then I've got your pressurized cabin. Again, it's like a capsule sealed. And then you've got a controller that allows you to generate, to meter the amount of air blowing in from a unit in the engine housing here that basically pressurizes the cabin. So typically it's going to be off a turbocharger or something like that. That's going to pressurize. It's going to pump air into the cabin to pressurize it. On there, and then you'll have these safety dump valves and outflow valves. They just regulate the amount of pressure. So typically what you're going to see, I think they've got a diagram here. Let me just see if I can find it. Yeah, here we go. This is it right here. So you can set the rate of climb of the pressure inside the cabin. Usually there's like a setting there. You can set it for 500 feet per minute. We know what a vertical speed indicator is, right? We've all seen that. And that just tells us the rate of climb. And typically, most people are not going to notice a 500 foot per minute climb or descent. That's a pretty shallow climb. So in the cabin, when we set our pressure, we're going to probably set it between 5 and 1,000. Then your ears can kind of adjust to it. If you fly with a cold or you have some sort of sinus infection, you're going to be much more, susceptible to pressure changes. That's why you hear a lot of times when you're flying on the airlines, I hear it all the time. People saying, "Oh, there's a baby next to me, and it was just bawling the whole time." Well, babies don't have developed, they haven't developed their sinuses well enough, and so for them, it's like a balloon expanding as they go into an aircraft. Sometimes if they're congested or something like that, it'll just expand and it causes pain, and they might have crying. So if you do hear a baby, crying, one of the things you can tell them to do if it's a young child, and a lot of young children have this too, if they can sometimes just pull their face back like this or pull on their ears, tug on their ears like that, that can kind of loosen up some of the sinus cavities and allow it to equalize the pressure on there. Usually after 10, 15, 20 minutes, the pressure subsides because some of that air is leaked out of their sinuses. It's not so bad, but it is painful. If you've ever gone up If you've got a cold, I don't recommend flying, especially at high altitudes. If you're just doing pattern work, that's not going to be a problem. But if you're flying at high altitudes, it can be extremely painful on there. So that just tells you right here, this cabin climb, this tells you, what rate you would climb. And typically, you're going to have like a little dial here that says, I want to climb at 500 feet per minute until we get to our cabin pressure altitude, which in this case is a little over 5,000 feet here. So this needle right here, there's two needles here. You've got your cabin pressure altitude. So let's say we're climbing to 15,000 feet, but we want to keep our customers happy in the back seat. We'll just set our cabin altitude to like 5,000. That means as the aircraft climbs up to 15,000 feet, the cabin pressure is going to feel like we're at 5,000 feet. Okay, the cabin differential pressure is the difference between this right here and the actual altitude that we're at. So if we're at 10,000 feet and this is pointing at 5,000, well, let's say we're at 12. We're at an altitude of 12,000 feet, and we've set our cabin pressure to 5,000 feet. What's it going to be our differential pressure? I'll take a guess. 10,000. Okay, and so we're at 12,000 feet, and we've set our cabin pressure to 5,000 feet. What's the difference between those?
7,000.
7,000. Yeah. So that's the differential. That's what they're talking there. So the differential pressure, the max that this aircraft can handle is around, probably around, probably around 4.8, somewhere around there, 4.8 thousand, so 4,800. That little dial right, that needle right there, that's just going to move. That's going to tell you the differential. So we really can't take this much beyond that. And that has to do with the aircraft. Indicator is attached to. Every aircraft is different. Some may have allow you to do, well, obviously airliners can have a huge differential, because they can fly up like 40,000 feet, but their cabin is pressurized at 10,000. So that means they would have a 30,000 foot differential. Panel. This is not cabin pressure. This is for oxygen supply. So between oxygen systems and pressure stations, pressurize. Now, oxygen systems take oxygen from typically an oxygen tank, and they deliver it to the pilot through either like a nose panel or a mask or something like that. So this would be oxygen flow regulator or whatever, and you could turn these on, activate them. This would be useful up to maybe like 26,000. Much beyond that, you really need to have forced air in your lungs, because your lungs aren't strong enough to draw in oxygen, even though it's being supplied to you. You can't inhale because there's just not enough strength in your lungs to draw it in. So they have to force in. Fighter pilots have to have these masks on their face, and they're tightly strapped to their faces. They've got those huge straps. You've seen it before, and they blow. It literally blows pressurized oxygen into their lungs so they can actually breathe. Without it, they don't have the strength, especially at the altitudes they fly at. Down close to the earth, and it's just like what we do here. We just breathe in. But it should be a good point to make here is that the higher you fly, the less oxygen is available, right? It's just harder. You're not getting the oxygen in your systems. There may be oxygen up there, but you're not getting it in your system, because you're not breathing in deep enough. So you really notice it at night. If you take a hit of oxygen when it's at night, you'll notice right off the bat that everything becomes brighter. So oxygen affects our performance. It also affects our thought processes and stuff like our brain. Our brain doesn't have enough oxygen to operate at higher altitude. But at night you can really notice it when you take like that hit of oxygen. You'll actually see everything just brighten up instantly, because the oxygen is getting into your bloodstream. It's getting to your eyes, and everything's performing a little better there. You guys have all seen these before, these continuous flow masks. This bag may inflate, doesn't always, but basically it's, you've got oxygen flowing into this bag right here or into this mask that you strap on there. Okay. Very common type of oxygen system you'll see on small aircraft. You can see this is the face mask. This is the nose cannula right here. And then some sort of regulator to make sure that they're getting oxygen there. It's a pulse oximeter. This just tells you how much your O2 is in your blood. These are dirt cheap. You can get them for like $10. Not a bad idea to have one of these in the aircraft. What this is telling you is it's telling you the oxygen in your blood. Right here, you've got the rating is like 98, which is pretty good. If you get down to like around 94, you're starting to get less oxygen. You can actually wear them on your finger and take it up to altitude and actually see the oxygen drop in your bloodstream. It'll actually drop while you're flying here, and then that's your heart rate right there. So again, that's a good thing to have. And there's several things we get into, and when we talk about aeromedical factors, we talk about this a little bit more with carbon monoxide, how that works, how it prevents oxygen from getting in your system. So that, obviously as human beings, we need to have oxygen to function. And there are several things that could prevent us from getting oxygen. One of them is carbon monoxide. Another one is not having enough pressure, air pressure, that or enough oxygen in the air. Those are all things that affect how we get oxygen in our system. If we don't have enough, we don't perform as well. We make poor decisions and things like that. Okay. Any questions on that? So icing types of de-icing systems here. So there are several different types. I think we're going to page 7-40. You've got, this is a type of de-icing. So let's talk a little bit about, first of all, the terms. You've got anti-icing systems and you've got de-icing systems. Does anybody know the difference between de-icing and anti-icing?
De-icing is removing ice, and anti-icing is preventing ice.
Very well put, yes. So de-icing takes ice off, already existing ice off of the wings or flying surfaces, whereas anti-ice systems helps prevent ice from even forming. So with that in mind, let's talk about some of these things. Like this right here is a bladder system. It's on the leading edge of a wing, very common with general aviation aircraft. They're very expensive. You're not going to, put one of these on for less than $30,000-$40,000, and probably closer to $60,000. But they're very expensive. And what it is just a strip of rubber, but it inflates. This is the inflated state. So this is the deflated right here. It's just basically flat rubber. Here you can actually see the tubes inflated here. Now how this works is, what happens is as ice forms on that wing, typically ice is going to form always on the leading edge there, so you get this this layer of ice that forms on there. What the pilot will do, if it's not automatic, they'll hit a switch, and these little boots, these de-icing boots, will inflate these little tubes in here, and it breaks off the ice, and it just falls back, and it keeps the leading edge clear of ice. It doesn't do anything for the ice that's already formed at the back here, but it keeps it off the leading edge. It's very important. I know any reasons why we want to keep ice off of the wings of an aircraft. Do you have an idea? Yes, yeah, it's for drag. That's one thing. Yeah, absolutely. Because as you build up ice, it creates it's actually changing the shape of the wing, and it's creating a lot of drag. Any other things that can happen there?
It creates turbulence, so decreasing.
Yep. Mm-hmm. Yeah, it actually, it just creates more drag. Yes, yeah, absolutely. Any other things? Ice weighs something, right? It increases the weight. And if you have like clear ice, that can put on, hundreds of pounds of weight very fast. Within a few minutes, you can put on several hundred pounds of weight on the aircraft. It'll just build up on the leading edges. So that's why we have these, de-icing boots. They're called de-icing boots. And this is a pneumatic system. Pneumatic stands for air. Okay, so air, you've got hydro, water, fluid, and pneumatic air. So these pump up, you hit a button, a little compressor turns on, pumps these up, the ice breaks off them, and it hopefully keeps the leading edge of the wing clear there. So let's see. Yeah.
Would it also decrease lift due to changing the shape of the airfoil?
Yeah, it definitely would. Yeah. So that gets back to drag. It adds, drag and stuff like that.
Then it could change where the pressure differential is.
Yes. Yeah. Yeah. I mean, it's changing the shape of the wing. So it's you're changing the whole wing itself is producing a different type of lift, probably not nearly as much, and it's not as efficient. Yeah.
Since it's less pressurized, would those be less effective?
That's a good point. Yeah, no, they wouldn't be because potentially they could be if the device that pumps air into this, but it's a sealed system, so it doesn't care what the air pressure is outside the aircraft. But at high enough altitude, that could be a problem. Because there may not be enough of atmospheric pressure for the system to work properly. But typically, the altitudes that they're flying, they've been certified to pump these bladders up. Yep.
Pressure decreasing well to the absolute fantastic. On the second one, one pressure to go potentially explode.
No, that's a good point. So yeah, the comment was, could these bladders explode from too much pressure? And no, they can't. If everything's working right, okay. If everything's working right, what will happen is there's a little pressure relief valve on these systems to prevent the pressure from exceeding a certain amount, which would potentially burst them. That would be a serious problem on it. So that's what is that, a de-ice system or an anti-ice system? De-ice. Anybody else? Yeah, it's a de-ice system. Exactly. Okay. Yeah.
So the question with that is, if you have like an airplane that DC-10,
Yeah, DC-10.
if those inflated and the ice fell off on the engine, since all the concern over here, could that damage your jet engine?
It certainly could. It certainly could. They have ways of mitigating that with jet engines. There are some ways of getting around it. As a matter of fact, there's separate systems, mechanical systems to prevent that. Foreign object debris from getting inside the engines, and we can talk about that later on. It's not something is relevant really to private pilot license, but when you get into jets, absolutely, you're going to have to learn the system. Yep.
Custom jet engines that
Yes, yeah, I've seen that on YouTube. So you can actually watch destructive engine testing, particularly with jet engines. They'll actually show frozen turkeys, as a matter of fact, I think are chickens or something like that. They fire at a real high rate of speed into these turning engines, the turbines, and the turbines just slice them off. But they have to do that because obviously they're going to be bird strikes, and bird strikes, obviously we know that it can be devastating. I think the Miracle on the Hudson, you guys remember that incident?
Yeah.
That was a case where both engines were struck from birds, and they couldn't restart the engines in time, so they landed
Don't they have
safely.
to make sure, like, in those destructive tests, they have to make sure the casing in cases.
Yes, yeah, the blades in there, yeah, older aircraft didn't have some of those protections. There was an incident, I don't know how many years ago it was, where a fan blade, so that the engine failed, right? But one of the turbine blades slung off the jet engine and punctured the fuselage, and then caused explosive decompression. I think a passenger was killed in this, but they got sucked out or something like that. So yeah, it does happen. With the newer engines now, they've got incredibly strong, material around the engine. I mean, they've got these massive, I think, I can't remember the name of the company. I think it was a European company that makes a gigantic engine. Gosh, I can't remember. What's that? Mercedes? Yeah. Rolls-Royce. That's it. Yeah, it was Royce. Yeah. They actually purposely, let the fan blades, these large fan blades, depart from the hull itself, and the engine will destroy itself, but it'll keep it contained in the engine, just blow all the parts in it. So yeah, they're very strong, but it is a potential problem. So yeah, all that to say is that ice is a potential issue for turbine engines as well as reciprocating engines. So we have to have some way of protecting it. So there's another thing. This right here is a very fine mesh. You're going to see it on the leading edge of a wing. And you can see that this fluid right here, that's not water. That's like kind of a glycol, I think, mix. It weeps. It actually weeps from the leading edge of the wing. And what happens is it prevents the formation of ice on the leading edge. This is the leading edge of the wing, just like, this right here would be like mounted right here. This would be the weeping wing right there. It'd be a strip on there. And you turn it on and it pumps out. And you'll see this in a lot of smaller aircraft, like the Cirrus SR-22 has this. I don't know if it's an option or it's included with the aircraft, but you can turn these on and adjust the flow rate of the fluid on there. Would this be a de-ice or anti-ice system? Anti-ice, yeah.
That also somewhat like the rest of the.
Yeah, and that's another benefit of it. So as it weeps out of there, it actually, and what it does is it actually flows back across the wing. Its main purpose is really to prevent ice from forming on this. There's pros and cons to each of these de-icing systems or icing systems. The typical pros and cons for a bladder type system like this, where you turn on a pump and then it inflates to this right here. What can happen, and I don't know how much proof there is of this, but basically, if let's say you get ice that forms on here, and you turn it on, it may just push the ice far enough away from the wing, but may not break off. That typically happens if you've got a very small layer of ice, you turn them on, and all it does is push the ice further away from the wing. It still stays attached to that leading edge, and then your icing become useless because the rest of the ice is just going to form on there. And again, I don't know how much proof there is of that exists, but that is a potential problem. These are also very high maintenance. Yeah. Mm-hmm.
It says that this is, so it says that although some residual ice may remain after a boot cycle, bridging, which is what you were describing, does not occur with any modern boots.
Yeah. Yeah, it is a potential issue. It's not something that's very common.
Okay.
So, yep. Okay, all right. So again, TKS, weeping wing, very common. The drawback to this is these can become overwhelmed. And if you get a good solid layer of ice on there, they may not do any good for you at all. So these are all ways to help mitigate, ice in the air. The bottom line is, if you go up and fly and you don't have any kind of de-icing or anti-icing system, you need to stay away from ice. So in weather reports, we'll find out, if there's potential icing up at altitude, and if there is, it's a simple decision. You're not flying. It's very simple. You just don't fly. If you don't have de-icing equipment. If you have de-icing equipment, it has to be certified to fly in those conditions that you're flying in. So if let's say that you've got, it's light icing, like lime ice, which is kind of milky ice, and it's very, it isn't as bad as like clear ice. Clear ice is literally that. It's just a solid layer of ice that forms. So if there's clear ice up there, that forms fast, and it also is very heavy. So if you have de-icing boots, let's say, you probably are not going to want to fly in clear ice unless you've got, some sort of, heated wings. Jets are got it great because they duct heat from the jet engines to the leading edge of the wings, and it just blows out air and it keeps the wings, free from ice. They've got the best. But even those can be overwhelmed. From time to time if you have extreme icing. So, yep.
For the icing boots, why don't they inflate periodically?
They can, yeah. On some systems, they're automatic. They automatically will, you know, inflate periodically. They'll just inflate on their own. Most of the time, the pilot controls it. They hit a button and it just cycles the boots on there. So, but you can on some systems you can do it. Set them up so that they do that. Another type of de-icing or anti-icing, say, is prop, and this is what's called a heated prop. You've got basically all it is just a strip of rubber, and inside that rubber there's a bunch of heating elements. And you can see here this is just at the root of the prop itself. And we want to prevent ice from forming down here because, for one thing, there's a lot larger surface there, so more area for the ice to stick to. But secondly, you know, as that ice breaks off, it kind of slings off the side there, and it'll keep, you know, most of the ice off here. It's really hard for ice to form on this. It can form on the thinner portion of the blade, but that thick portion is really susceptible to ice, and that's why we have these little boots that you know, cover the root portion of the prop. There's the root there, and this extends out to the prop itself. But these obviously are driven by your electrical system, so you have to have a really good, you know, alternator or generator to generate the amount of current to heat those elements there. So, yeah.
Would the same trick to the force of the propeller just launch the ice off the birds?
Not necessarily. I mean, if it's like clear ice, once it hits that, it's stuck to it really hard. I mean, it's you know, even rime ice can form on. It's not as likely, but clear ice is very dangerous. And you can imagine, you know, this blade is turning at a pretty high speed, close to the speed of sound on the tips. So you know, in a situation like that, you know, you really don't have a lot of options. So having that heated blade, it is going to heat, you know, the blade further over here, but it really is designed to get the ice off of that lower portion there. So, yep.
Follow up to that, if the heated part, since it's right there,
Mhm.
the ice, would that come off and hit the stuff that's towards the
Okay, so the question is, you know, if you turn this on, what happens to the ice? Does it sling off? Does it hit the aircraft? The answer is it can hit the aircraft. I was flying on a twin a number of years ago, and we had some ice develop on one of the tips of the props. And you know, a twin engine, you've got the engines are right here and right here, right? Well, when that ice slings off those props, where is it going to hit? It's going to hit the fuselage, yeah. So if you look at the side, most aircraft, twin engine aircraft, are going to have like a plate somewhere on this side right here, because you know the engines are rotating like this. Well, they have a tendency to swirl the ice, you know, against that. So there'll be like a little protective plate on this side of the aircraft on a multi-engine aircraft. And depending on how it's configured, if it's counter-rotating props and things like that, all those things will affect it. But typically, you're going to have a protective, you know, plate right there. Otherwise, if you look on a twin, you can do this. Go to any twin and look roughly where the line of the prop is. You know, where the rotation, plane of rotation, and look on the fuselage, and you'll see actually if that aircraft has ever had ice, if it's ever been in an ice situation. You'll actually see dents on the fuselage itself from the ice swinging off there. Yep.
Getting the ice off, even with the ice systems.
Yep.
That's how you want to roll like that.
Yeah. So the comment was, can you get ice off of, if you didn't have de-icing systems, can you get ice off of the aircraft by shaking it? And the answer probably is never. It just, you know, it's possible if it's just about ready to fall off anyway. But you have to keep in mind that an aircraft, you know, if it's traveling through the air 100 miles an hour, that's a lot of pressure on the ice. And if it doesn't fall off at 100 miles an hour, it's not going to fall off if we shake the plane at all. Now, what may happen, you could maybe try doing a side slip. I wouldn't recommend it. You know, you can do a side slip or forward slip, that is. And see if you can get the airflow to change. You know, maybe that'll pop some of the ice off. But if you're in a situation like that, that means that you didn't do enough planning ahead of time to, you know, to stay out of the ice. So if, you know, but again, you know, let's say, you know, you're flying with somebody else and they made the poor decision or whatever to fly on ice, and you don't have de-icing equipment, you can try anything at that point. The general rule of thumb is if you get into ice, you need to either climb by 4,000 feet or descend by 4,000 feet. That's generally going to get you out of icing conditions. Not always, but it's, you know, if you're at a high altitude, if you can descend, you're going to descend into what? Warmer, colder air. And typically it's going to be warmer air. The closer you get to the Earth, it's going to be warmer. The higher we get, less pressure, cooler, you know, it's colder up there. So as a matter of fact, it's standard the way that works. So, okay. Any other questions on that? All right. So let's move on to flight instruments. Let's see what we have for time here. Okay, 9:30. All right. All right. All right, flight instruments. I think we've kind of reviewed some of this stuff already. Let's see here. Let's talk about, first off, let's just talk about the 6-pack. This is what we see inside the cockpit. This is a typical, you know, steam gauge panel right here. You've got this right here. What is this instrument? Yep, it's an airspeed indicator. This one right here. Attitude indicator, right? What else is it known as? Say it again. Artificial horizon, correct, yeah. This right here, it's an altimeter, yeah, altimeter. Yeah. And this one right here?
Side slipping.
This right here is called a
Turn coordinator.
turn coordinator. There is a slip and skid indicator. That's different though, okay? Turn coordinator just tells you the amount of turn. Well, actually, what does it tell you? What does a turn coordinator tell you? You know, this bonus points. This is not something unless you guys have read ahead. So, what does a turn coordinator tell you?
It tells you whether you're slipping or skidding.
Slipping or skidding, okay. And actually, that's what is this right here? Does anybody know what that little device is right there? Yep.
Showing the
What's the name of it though? It's called an inclinometer. Okay. And it does show slipping skids. Yeah. But what does this right here show? Anybody else? What does it show?
The plane.
No, it does not show the bank of the aircraft. That's wrong. Okay. What does that show? And this is that's all right. Everybody gets this wrong. Everybody gets that wrong. Everybody always thinks, okay, well, that's just showing the bank of the aircraft. It does not show the bank.
Is it showing?
No. It shows your rate of turn. Okay, if you look down here, it'll say something like 2 minutes. You see this like here, this little right here? It says 2 minutes. So what that means is if the ball is centered right here, that means our center of gravity is below us. It's not shifting off to one side or the other. Okay, and that the wings turn to this level right here. That means in 2 minutes you'll have done a 360-degree turn. That's all it's showing. This is really important because you're going to get this on the test. The FAA will probably have a question on this. How many degrees of bank is this turn coordinator showing? Turn coordinators do not show bank. They show your rate of turn. Okay. What does show the amount of bank? Attitude indicator. Yeah, right here. There's 10 degrees of bank, 20 degrees, 30. This right here is 60, and that's 90 degrees of bank. Right there on the attitude indicator. This just again indicates our rate of turn. Okay. What about this one right here? What's this known as? Just go ahead and say it. Heading indicator. Yeah. Or also known as, anybody know the other alternate name for that?
Vertical compass.
Nope. It's not a vertical hard compass. It's okay. Well, first off, is this a compass?
Yeah.
Does it use the magnetic?
No.
No. It is not a compass. Very important. This is also known as a directional gyro. It's a gyroscope. It is not driven by any kind of earth. It's not driven by a magnetic field of the earth. It's actually a gyroscope. Does anybody know what other instrument is driven by a gyroscope? I mean, say again. Yeah, artificial horizon has a gyroscope in it. Is there another one here that's driven by a gyroscope? Yep. No, vertical speed is not driven by, that's driven by air pressure. What's another instrument that's driven by a gyroscope? Go ahead.
Turn coordinator.
Turn coordinator. Yeah. It's got a gyroscope in it. And, you know, we've got enough time. Let me just get this out there. Right.
So it's good. I showed you guys that gyroscope last time.
So let me show you how a turn coordinator works. Let's get a welder to spin up here. All right. So this is a gyroscope right here. It's got a little spinning wheel in there. You can see that. It's kind of hard to see, but this is a precision gyroscope. All right. So what I'm going to do, I'm just going to spin this up. Now keep in mind that the gyroscopes in an aircraft engine they typically spin it around 20,000 RPM, which is very fast. This is only going to spin around maybe 10,000. We can get it up to that speed there. So I'm just going to get it spinning here. You probably can't hear it, but it's actually starting to spin up the. Can you hear it?
Yeah, it's
Yeah.
Sounds great.
sounds like a propeller actually.
Yeah.
In the distance.
That's all I want my house to sound.
Okay. All right. So I'm just going to pull this off here real fast. All right. So now the gyroscope is spinning. I'm just going to cage it here and put it on my hand and see how it moves back and forth and the gyroscope is staying level. That'd be like the plane. That's how a gyroscope works. But what we can do is we can put it on its side and I can try turning, and notice how my hand represents the aircraft. As the aircraft turns, the gyroscope pretty much wants to stay, you know, pointing in that direction. So as I turn, that's how our gyroscope works. The rate of turn, or the turn coordinator itself, it's mounted slightly differently on there. I think it's like this. And then as you turn it, it indicates how much you're turning through here. We won't get into it. I think they've got a better diagram to show how that works there. But that's essentially how a gyroscope works. It uses a principle called rigidity in space. So it wants to stay the same position in space as you move the aircraft around. See how it's just staying right up there. And we notice it's starting to wobble now. That's called precession. That happens because of friction and stuff like that. There are forces acting on it. But gyroscopes are absolutely fascinating. There's some really good YouTube videos if you ever want to see what's a little bit more details on the gyroscopes. So let's get that out of there.
So with that being said, could you use a gyroscope to turn? If you manage to figure out like a way to control it, to be able to use it
The ISS uses gyroscopes.
Yes, yeah, actually a lot of satellites use inertial gyroscopes. So what they do basically, they'll spin a gyroscope and it exerts a force on the satellite and it gets it to turn. But they have a bunch of gyroscopes on there. If they spin it, it's going to exert a force on it, causing the satellite to either turn or whatever. It's not going to move it through space. You can't use gyroscopes to actually, at least as far as I know, to produce a forward momentum. But it's only designed to, if we're pulling something up and let's say there's a little spinner on this side in space, it's going to want to turn, based on how a gyroscope particularly works. Yep.
If you had a gyroscope in space, would it just stay in the exact same spot since there's no actual weight to it?
Theoretically, if there is no friction at all, zero friction, the gyroscope,
Would never stop spinning.
it would never stop spinning and it would stay in its perfect orientation. But as soon as you exert some force on it, a brake or something like that, or pressure on one side, it's going to transfer that energy into the motion of the gyroscope. It's beyond the scope of what you need to learn here. If you want to delve into gyroscopes, there's some really good videos on it. And I don't know all the characteristics of gyroscopes other than to tell you that, if you spin it really fast, it wants to stay at that position. It really wants to resist moving out of it. If you spin it real fast, it's not just going to go like this. It stays up, just like those toy tops we had if you ever had a toy top when you were a kid, that's how they function. You know, you spin it and they just stay upright like that. And then over time, due to friction, they'll start wobbling like this. And that's you know, caused by, you know, friction and stuff like that, and then recession in there. So, yeah.
So there is actually a car called the Gyro X
Mhm.
that is on two wheels and uses a large gyroscope
To keep it
in
steady.
front.
Yeah.
Yeah.
Yeah. So the what is it? Those walking things, what do they call the segways? You guys ever seen those? Those use gyroscopes to just, you know, they're just two wheels. Hoverboards probably, yeah, they probably use gyroscopes. So the more weight you have on a spinning gyroscope, the more stable it is. Yeah, Doug.
There's a sign for a monowheel, similar, have two gyroscopes that would rotate, probably, go against the turn.
Oh, interesting. Yeah.
Or something, one side of that.
Yep. I think, yeah, I think I've seen some of those monorails. Basically, just as like two wheels on a rail, and they had massive gyroscopes. The heavier the gyroscope, the more stable it's going to be. The faster a gyroscope spins, the more stable it's going to be as well. So, you know, again, this gets into areas that we don't need to discuss here. But if you want to delve into it, again, a lot of good YouTube videos. So, all right, so let's talk about the pedostatic system. So just a common mistake a lot of people make is, you know, they call it a pilot static system. It's called a pedostatic system. Don't make the mistake of saying pilot static. It's pedostatic. So let's switch over to, so again, let's switch back here. Steam gauge is right here. That's our vertical speed indicator. It just tells us in hundreds of feet how much we're climbing or descending there. Oh, yeah. Before we get into pedostatic, let's actually go over to the a glass display. This is something you typically would see in an aircraft. It's the same as this. Shows you all the same information, but it shows it in a slightly different representation. We went through this before. You've got, you know, on a technically advanced aircraft or TAA aircraft, you're going to have what's called a primary and a multifunction display. This right here is your primary function display, or what's called a PFD. It's going to have all of the same instruments that you're going to see with your steam gauges. And we need this, obviously, if we're flying in the clouds or something like that. You have to be able to see what your horizon is to stay level. So let's take a look at the different components and compare and contrast between a steam gauge and electronic or TAA, or a technically advanced aircraft. Over on this side, we've got our altimeter, our airspeed indicator. That's the same as this right here, airspeed indicator. And this tape moves up and down as we fly. Change our airspeed, it's going to change there. This right here, is anyone want to take a guess at what this is displaying right here? Just go ahead and say it.
Altitude.
It's altimeter. Yeah, that's our altimeter. It's called a tape. You've got your airspeed tape here. You've got your altimeter tape here. What about this tape over here? Yeah, that's our vertical speed indicator. Exactly. Yeah. And then this right here. See it nice and loud so I can hear it. Yeah, it's your heading indicator, directional gyro. Basically, this is what you're seeing. It's not a compass. It is directional gyro or directional indicator there. Okay. And then this is the equivalent of this right here, our attitude indicators. So we're seeing that they're massive. Just it's like flying a flight simulator when you fly an aircraft that has one of these, and you have these big displays. Just makes life a lot easier. Everything's at your fingertips. There is a big difference. I'll get to you in a second here, guys. So there is a big difference between this system right here and this system, and that is what we call glance value. So what's nice about the old steam gauges is you could actually glance at a gauge and see if there's a trend changing up or down or whatever. Whereas these, it's not as apparent. The glance value is a little bit harder. You know, you have to look for it a little bit more on these types of displays. Here it's super simple. I can just almost with my peripheral vision, if I'm looking at the airspeed indicator, I can see that the altimeter is changing, or my vertical speed. Not so much so with a display like this. It's a little bit harder to see. You'll see numbers rolling here, but you're not going to see whether they're going up with your peripheral vision right here. You have to look at that instrument. So there are some pros and cons to both systems. Most pilots trained on these old steam gauges. Now, newer pilots are starting to train more often with these nice, displays, these technically advanced aircraft displays, or PFD, primary flight display. You will put out a test. They are going to talk about PFDs and MFDs. MFD stands for multifunction display. Okay. All right. So let's talk about what drives those systems. So they both have the same inputs. They have static and dynamic air pressure that go into these. They may or may not have. We'll stay with that. So we've got the static and dynamic pressure that's pumped into the system, or actually brought into the system. On aircraft, we have what's called, they're all going to have what's called a pitot tube. So let me just, let's see if I can do it. For example, let's make this. So I don't know if I can, I'll try it like this. So right here, I'm just going to hold this like this, and I'm just going to blow on that. Watch what happens to that. Okay. That's a very simple airspeed indicator. If I blow on it for a long enough period of time, this will just stay up. So let's do it right here. And you can see how it kind of pushed out like this as I blew on it. If you're flying through the air, this is obviously going to push back. If I'm going this direction right here, this is going to push back like this. And we kind of have a gauge. We can put like a sheet of paper behind it with graduations on it, and we have a rudimentary airspeed indicator. So this is dynamic pressure. Again, this pitot tube is what captures the air. So what's happening here? This is pointed into the flight path right here, or on the leading edge of the wing. Let's see what here. I think. Well, actually, let's go to our simulator here. This one. We'll just go on the outside of the plane here and look at this and see if it. Yeah.
Is this a new simulator?
I know this is X-Plane 12. It is the latest version of X-Plane 12, though.
Is this one on the other simulators?
We use X-Plane 11 on the SIA sims. The big one that's in our office, the SIA office, is X-Plane 12. And yes, it's not as good as Microsoft Flight Simulator as far as graphics. Right. So I bet you it's we're floating. So let's see if I can. I don't know if I can take off here. I don't know if I can. Yeah, this is. I don't know if I can. Brakes. Yeah, I'm at full power. We're in the water here, so this is going to be interesting. Yeah. There we go. Oh, maybe it is a full plane. Yeah. I just want to get up in the air. Nuts. Yeah, we are.
No, it's not.
Okay. So, okay. Let's. Yeah, so it's in demo mode because I don't have internet connection on here. If I had an internet connection, I could do this. Let's do this. And
that one doesn't have
try this one again.
launches.
Choose location here.
Launch a passenger.
Should be a. Let's see. We'll see if here we go. Let's do this. I think this one might be up in the air. Was it in the air?
Yeah.
Yeah, here we go. Okay, good. So let's unpause it. All right, so okay, so let's just pause again here. So what I'm going to switch to the outside view here. Let's see, circle view. All right, so I'm going to show you on this aircraft the pitot tube is. Let's zoom in really close here. And it is right here. Do you see that little thing that's sticking out there? There's a little opening right there. That's the same, that tube right there is the same as this tube right here. So let's focus on how this works. So this is what we call ram air. That's the air coming into the wing itself, into the pitot tube. It's going into a chamber here. You've got little heaters right here that prevent ice from forming on the pitot tube. And that can happen if this seals up. we don't all of a sudden have any more dynamic pressure, any more air blowing into this. So let's take a look at this. Now, as I was blowing on this, blowing on this thing and pushing that out like that, that air is doing the same thing here. It goes in here, and the leading edge, it's blowing in here, and it's going to the airspeed indicator. And it's doing basically that same thing. It's pushing that needle using similar methods. It's not the exact same thing, but it's basically pushing that because there's pressure on it. So if I blow on this again, you can see that move. That's kind of what's happening here. Air is coming through here and blowing into this instrument, and it's causing this needle right here to move, giving us an indication of what the airspeed is. Yeah.
So this is like simple formula, like inflating a balloon, the amount of air pushing.
Yeah, it depends. In an aircraft, we'll get into that, but it uses what's called aneroid wafers for a lot of these instruments. So the more air pressure you have moving in here, the more those little aneroid wafers will expand. But there's more to it than that. So let's we'll get into this here. So you've got air blowing into the pitot tube. That's dynamic air pressure, right? Okay, and it's again, dynamic meaning changing. You know, you've got air blowing directly into it. It's hitting that airspeed indicator. The pitot tube only needs to drive the airspeed indicator. It doesn't need, it's not needed necessarily for these other instruments like the vertical speed and the altimeter. Those are driven off of what's called the static port. And that's on the side of the fuselage of an aircraft. So if we go back to our flight simulator, let's take a look here. And let's see if they actually model that. They may or may not. Let's see here. Usually it's going to be on. Sometimes they mount them back here. There's just a little, I don't see it anywhere here. Usually it'd be like in here somewhere or in the back. Well, here, don't see it. It could be, yeah. They usually model that though. Now let's see if we can zoom in here and see if there's like a little.
What's the difference there?
This right here, that's a ID plate there. It'd be somewhere on this line right around here. There'd be like a little circle. It's not very large, and it's very dangerous if you cover that static port up. But typically, it's going to be mounted somewhere on the fuselage up here, and it's mounted. It's not pointing into the slipstream, into the flight path. It's mounted perpendicular to it, and that's because we want static air pressure. We want the ambient outside air pressure. We want to measure that. We don't want to measure the impact pressure like a pitot tube. So the pitot tube is measuring that impact pressure as the aircraft flies through the air. We're measuring that. Whereas the static port is just measuring the outside air pressure. So we don't want that impact pressure. So that's the difference between the two. So the impact or ram air pressure drives the static, the airspeed indicator here, and the static port is just to measure what the air pressure is outside. Okay. And then there's also what's known as an alternate static source. That might be something inside the aircraft, and it could be something as simple as, you know, if let's say you lose your static port and becomes iced over, or a bug gets in there or something like that. It'd be unlikely in flight, but on the ground, dauber wasps sometimes will nest in those little holes. It's a perfect hole for a nest for them, and they'll cover that up. You should catch that when you're doing your pre-flight inspection. It's so important that it's on every checklist to check the static port and make sure that it's open. But if that does get plugged up in flight, you can do another thing here. We could just break the glass on one of these instruments. You want to probably break the glass on the cheapest instrument, the altimeter. I would not want to break the glass on that. It's very expensive. I mean, you're talking thousands of dollars for a good altimeter. Vertical speed indicator you can get for, you know, much less expensive than that. But what I would do is I'd probably just, if this got iced over and I was really in a dire situation, I was in the clouds, in ice, in a situation that I should not have gotten myself into, let's say, I would break the glass here, and now we've got static air pressure. You're letting just the atmospheric pressure. This will only work on a non-pressurized aircraft, though. If you're in a pressurized aircraft, that's not going to do you any good, because the pressure in the aircraft is going to be different, right? change it. So you can't, for small planes like this and that one behind us over there, those single engine general aviation airplanes, that would work. Yeah, Danny. Sorry. I say it again. No, it won't change it, but your static pressure is measuring the outside ambient pressure, so the atmospheric pressure around the plane itself. If you put this inside of a pressurized aircraft, all it's going to do is, the altimeter is going to descend down to the what your cabin is pressurized to, which is not accurate. You're not going to know what your true altitude is. Yeah. Mm-hmm.
So if you broke that, and very high,
Mm-hmm.
could that cause the static port to unclog due to the pressure?
Well, this is, you shouldn't have to go, but I see what you're getting at with it, but it is possible that it could pop it out. It would be, because especially if you're in a pressurized air, if you broke that, the pressure in the aircraft would try to escape through that static port if it's plumbed that way. But it may not be plumbed. It may be a electronic, instrument. Like most of the aircraft today now, you can't, obviously with a TA aircraft, this one, you can't break the screen, and so that would be a very, we're talking about tens of thousands of dollars. This is only works for the older style gauges. So again, there's our vertical speed indicator. I would crack that glass if I had to. Again, this is, you probably won't see that on the test, so we'll just move on here. So this little piece, this is like a little plate. This is maybe like an inch and a half diameter plate, and then you got a hole in the center of it. And you can look on the aircraft. If you go out to the flight line, you'll see the port on some of these airplanes. You'll have to look for them. They typically look very similar to this right here, just this little, looks like a quarter with a little hole in the center of it. But they've got a strong plate around them. That's a heater. And what that does is it heats up and it melts off any ice or anything like that. You get into icing conditions, you'll turn that on, and that'll prevent ice from flowing through the system there. So here have static source. If they do have a switch for an alternate static source, then you would just turn that switch on. You don't want to break the glass in one of these things if your aircraft does have an alternate static port. What's that? That would be a worst case scenario. Yeah. You don't have, let's say you're in a really old aircraft, you get stuck in icing conditions again, which you shouldn't do. I mean, you should never be in that position, but let's say something just really bizarre happens or whatever.
Why don't planes have multiple static ports?
Some of them do. Yeah. Like airliners have, at least 2 of them, maybe 3 or 4, on the aircraft, and they'll have alternate static sources, stuff like that. But most of the time they have, they'll have at least one. General aviation will typically have just one aircraft or static port there. Okay. The pitot heater, so that's going to heat this tube right here. Again, ice can form on that tube. You got little heater elements. You turn this switch on. This just warms that pitot tube up. It's so important that it's in every checklist. You have to, turn on the pitot heater, and you put your hand on that pitot tube. It gets really hot. You'll burn your hand on it if you're not careful. And in some aircraft, you'll actually, if you leave that on the ground on a warmer day, like over 40, 50 degrees, you'll actually burn the heater out. So that's how strong they are. They're very powerful on there. So let's see. Yep. Ram air, pitot heater switch. Interesting. I think that's everything there. So what's that?
Drain hose?
Yes. So drain hole is there just to drain out water that gets into the pitot port right there. So if you get, let's say you get some ice in here, you turn on the pitot heat, it's going to melt the ice, and then that's going to just get sucked out from these static holes here on there. If that gets blocked up, then your airspeed indicator is not going to show anything essentially. So okay. Altimeter. So we go back to here's our diagram. There's our altimeter right there. It's driven off. This blue stuff is all the static, is what drives the static port. Notice that the airspeed indicator, you have a static air and also dynamic, or the ram pressure air going to the static, to the airspeed indicator. Whereas vertical speed and altimeter have just static. You will see that on the test. They're going to ask you about this. So static air pressure here and here, going to just those two instruments, but ram air is going to the airspeed indicator. So pitot feeds the airspeed indicator, and static feeds the airspeed indicator. These others are just static air pressure. Yeah.
It shows us software back.
Actually, I am having a hard time
It
reading.
shows us software back.
Hey guys. No. Okay. Sorry.
It shows us like software back. Back to this. So it's not a.
No. No, they wouldn't. They wouldn't be connected to a system at all. Yeah, and that would be, you're thinking about the gyroscope, the vacuum gyroscopes. The vacuum systems typically drive the gyroscopes. They won't drive any of the vacuum, flight instruments. These right here. These are strictly used outside. They're, no very little. They wouldn't use any electricity other than for lighting and stuff like that. Obviously, on a TAA aircraft, you're going to have, these are going to be driven with little sensors, but they'll display that information on top there. Okay, so let's go here. So let's take a look at the inside of an altimeter. So the altimeter is, again, very basic design. These are aneroid wafers right here, and what they are, they're basically a balloon, but it's a very sturdy balloon. It's a sealed air. As the outside air pressure decreases, what do you think is going to happen to the aneroid wafers? They're going to expand. Yeah, exactly. And as the air pressure increases, they're going to contract. Yep. And through these linkages right here, they will drive these dials here to use an altitude. So it makes sense if you're at a high altitude, low air pressure, in this cavity, the cavity around those aneroid wafers is also they're expanding, and it's where we indicate higher altitude there. As we descend, these are going to contract, and through these little series of mechanisms right here, it's going to turn these dials, and it's going to show a lower altitude. Okay, it's a simple concept, but you will use this all the time in aviation to solve problems. Just remember, this cavity around these aneroid wafers. Again, that's the outside static air pressure, the ambient air pressure. Okay, that's what's supposed to be going in there. Again, you can see it here, static port going in there. If that static port becomes blocked, then this whole case is, obviously this altimeter is not going to work the way we expect it to. So, okay. So there's several components to the altimeter. Does everybody know how an altimeter works? Maybe we should just go over that real quick on how they work. So let's just take a look on their simulator here. Let's go back into the. Okay, what I'm going to do is. All right. So for an altimeter, we've got several different needles on here. So you've got this long needle, a very short stubby needle, and then another long solid needle. Okay, they all serve various functions. So this small needle indicates thousands of feet. Okay, so if this is pointing between 2 and 3, it's somewhere between 2 and 3,000 feet. Okay, this long needle is hundreds of feet. So here we can see it's pointing around 6, so it's 600 feet. So what is our altimeter? What is our altitude on the altimeter? 2,600. Yeah. Again, this one is always pointing to thousands, so it's 2,000, and this is hundreds, so it's 2,600. Now, this right here is for 10,000 feet. So if we were at 12,600, where would this little needle be? What do you think it would be? It'd be just past the 1. Yeah. Okay, because it's 10,000s. So again, hundreds, this is hundreds of feet, thousands of feet, 10,000s of feet. So You will see this on a test as well. So they're going to give you various indications of altimeters, or altimeter diagrams, whatever pictures, and they're going to ask you, what is this altimeter showing you? And one of them shows this over 1,000 feet. And the common mistake for most, pilots when they take the test, they're going to say 2,600 when really it's 12,600. So don't make that mistake when you take the test. Make sure you know how to read an altimeter. Okay. Yeah.
So is there any aircraft out there with a 100,000 feet?
Unless it's a spacecraft, maybe the SR-71. It's possible. Yeah. It's again for general aviation aircraft, it's not relevant. You're going to see this type of altimeter. This is the most common type of altimeter you'll see in an aircraft there. So yeah.
Into group space.
It would. Yeah, it'd probably be more closer to 600,000 feet. Yeah, it's several miles. Yeah, and again, it's not something we have to worry about. Unfortunately, Yeah. Anyway, yeah, Donnie. Hey, you guys, just a second. Okay. Yep. Sorry, I can't hear when.
I accept general aviation aircraft. Utilize
Yeah, vast majority of them are not. Small aircraft are typically going to stay below 10,000, but you can all of the general aviation planes I've ever flown are capable of flying over 10,000 feet. Is it practical? Probably not, because it's going to take forever to get up there. If you're doing a long cross-country flight, there may be benefits to climbing to that altitude. So, it is possible that you'd go up there. All right, tell you what, guys, let's take a short break here. We'll do 10 minutes, and then we'll dive back into this, into the instruments here.
What are we talking about simulators?
It depends on how much progress we make here before we go to the simulator. So there's a possibility we may be there next week. I'll let you know on the emails that I send out. Let's see. Be real careful with this. This is really expensive. Yeah. So let me get it spinning for you first. There's a trick to it. Getting it to spin up. I'm gonna get the battery set up here. Actually, I should just turn this down. If you can hold on, just keep right next to it. Don't pull on too much. The cable is just gonna. When I tell you, I'll actually turn that power switch off. Okay, turn it off. All right, there you go. And actually, try not to touch the thing there. You can actually feel it. See the force of it? You can actually feel it. Don't let that drop. That's very expensive. Yeah, be super careful with that. Like I said, it was very expensive. And you can feel the force of it, right there. It's resisting that change in direction there. How's it going?
This.
Switch, yeah, going easier for you to do. It's something I probably should use more of, but
So, what's really funny?
what's it?
So far, we've done multiple pictures in the aviation manual that are incorrect.
And what's this now?
In the PHAK.
Uh-huh.
Yep. We saw one.
Fit right here,
And also-
648.
Oh, yeah, yeah.
And then
Mhm.
you need to
Some of it is, this is the, what we have on the screen here, I think is a later version of the manual. They update these, and so some of these, sometimes the figures are, they don't match up with what you have here, so.
So this one right here, vortex is spinning the wrong way.
What's that?
The vortices are spinning the wrong way.
Let me see, what page is that on?
5A.
H.
It's right, yeah, he's actually the wrong, right down there and there.
Yeah. The lower question is spinning more the higher question.
It's hard to see in this diagram though, but this is the way the vortex is. Oh yeah, use your color. Yeah, that's actually correct.
Yeah, this is.
Yeah, I mean, that's a good point. Let's see. So yeah, it is coming down. It's like these, what is shown here is that as it rotates like this column of air is moving up, and the other side there, that side is moving down. I think it's just really hard to see on that, the way they've got it. The net effect though is that the air it's rolling, because it's rolling, one side is up, the other side is rolling down, and that's what they're trying to illustrate there.
It starts on the top side.
Mhm.
When it's on the bottom side.
Yeah, coming up, yeah. Yeah, that's a good point. So, and then maybe they'll change that and fix that, so.
It's just funny.
Yeah, uh-huh. Here's,
Future chapters, you can probably be going tomorrow, but you go to.
no, yeah, but I mean, we do talk about it with the aircraft performance a little bit. We get into there, we'll get into some of the details there, yeah.
That thing right there, the phone one, is that phone?
This one here?
Yeah.
Uh-huh.
If you take out the phone, kind of like this,
Uh-huh.
or push your phone,
Uh-huh.
like that, and try beyond the fact by putting the that at an angle, so ground effect would keep it aloft. And it's like I've seen like toys of those.
Were they just like, get it to
Run-
glide around the ground?
Yeah, you
Uh-huh.
run behind.
Really?
Yeah, it's been-
That would be, if you have a YouTube video that it can email it to me. Street ball? Okay.
Because
Yeah,
I
that's,
made like a forever one as long as.
Uh-huh. yeah, that's fascinating. I would, I'd like to actually see that, so. Yeah, Mark.
An opportunity for you if you want.
Yeah.
This truck just arrived.
Uh-huh.
He's in Garrison,
Uh-huh.
he said that because he had class going on,
Yeah.
he didn't open the aircraft if you want, and students come on closer.
Wow, okay. Yeah, and that would be, if you, okay, so, here's the problem, so. We've got just, it's gonna be like for the next 10 minutes here. So they would actually do it right now?
The crew just got it.
Okay,
I asked the guy who got it.
okay.
I said, "Well,
Right.
no."
Okay, yeah, but let's do this. All right, so you guys, we have a really unique opportunity. There's a jet out front here, and the pilots are willing to allow you guys, as long as everybody's really well behaved, listen to what they say. If they say don't touch anything, don't touch anything. All right, but they are willing to let you guys go out there, probably one or two at a time, to go inside the jet and see basically, this corporate jet in there. So if you want to, you can go out there. It's probably going to take 10 minutes. We only have about 10 minutes, so make it as quickly as you can. You can go in the aircraft, see it, and then come back right to this room here, and we'll get started again. I'm sorry about this, people at home. I'll see if I can maybe transition to my mobile, and I'll show it to you on there if I can. Otherwise, we'll get back here in about 10 minutes. So sorry about that, guys. All right, let's go out there while we've got the opportunity, and we'll let the guys. Oh, I know. Yeah, but yeah, that's going to change here momentarily. Okay, for you people at home, I do apologize for that. I wasn't able to get the phone set up. Yeah,
Is that the AP or the no the
APU,
no other one?
static. You know,
No,
static.
the on the outside, like the generator. Is that noise?
Yeah, it's a GPU,
GPU,
ground,
yeah.
ground power unit.
Absolutely.
Yeah. All right, let's dive back into this, guys. Let's see if we can get through here.
This was all this was it.
What's it? No, I know we're missing some people. We got to keep moving here. So I don't want the people at home to be waiting for us forever here. So, all right. So take your seats if you would. All right. Yeah, it's gonna be a little noisy here for a while. So, all right. So there is some there. The altimeter obviously works based on ambient air pressure, right? You guys, I need you guys. Okay. Yep. So obviously in outer space there is no pressure because there's no air molecules up there. At high altitude, it's thinner. There's some molecules there. And then low altitude, the air is much denser. It's, you're going to have more air pressure out there. So that affects how the pedostatic system works. All right. So we know that the static port is going to, detect that. Obviously, it's going to show it in the altimeter and the vertical speed indicator. But the airspeed indicator, because there's less pressure in there, or the air is less dense at higher altitude, it's going to read slightly lower. So the higher we go, the lower the airspeed is going to read. Does that make sense? Again, the air is less dense. If those aircraft may be flying at 100 knots, true. I mean, actually, maybe flying true. Not ground speed. There's a difference between ground speed and airspeed. There's different types of airspeed. There's calibrated. We'll get into that here in a second. But so if the aircraft is flying at, let's say, a true speed, the indicated airspeed might be much lower. They say like 90 or 80 knots, depending on how high you are. Again, it has to do with the density of the air. Okay. And that's one of those drawbacks with it. I mean, all these instruments do a pretty good job of representing the information that we need to see in the system, but they do have their drawbacks. And that's, for the airspeed indicator, that's one of them. So you have indicated airspeed, which is what the pitot tube is actually reading off of, what it's actually reading off the pitot tube, and you have the true airspeed, which is again what your real airspeed is at an altitude. So the closer to the ground you are, the closer to true airspeed you're going to read it here. Let's see, right? Yep.
So if wind was pushing you, would you could increase your airspeed orders?
I mean, it could have to be really strong wind. You'd have to be doing like 40 knots or see, but you probably see the airspeed indicator move around a little bit with if it was blowing right into the pitot tube. Yeah.
To make sure it's like or take off lower.
I recommend it, but it's something you could do to test it. So the mechanics and NPs with inspection authorization have equipment to check I should say avionics technicians would probably have the equipment to check your pedostatic system. And they actually do that. They actually have a device that applies pressure on the pitot port, and they measure to see if there's any, linkages anywhere that might, cause deviations and, accurate readings and stuff like that. So, but they'll actually test, that's actually required to be done for aircraft that are flown in IFR conditions. For VFR aircraft, it's not, required, but, for IFR aircraft, you have to have a pitot-static check every 2 years. And that's may actually do what you're saying there, yeah.
My book doesn't have on switch for the switch for that.
This right here? Yeah,
It's just model. It's the model.
yeah, depending on the book you have, it may or may not have it, but yeah, it is there. Like all aircraft, and you may have a pitot system. Keep in mind, you may have a pitot system that doesn't have a heater, so it may not. There's some aircraft that don't have pitot heaters. In the back, usually they put it. Yeah, they may have a pipe in the back or a little opening in the back there to drain out. And, so actually, again, if you think of a pitot tube, all it is like it's like a straw that's hanging out in the flight path of the leading edge of the wing there. It's all it is designed to do is to measure that or capture that impact air. The faster we're moving, the more air that's moving through that tube, right, and pushing on the dial on the airspeed indicator. Okay.
If you have a high AOA,
Mm-hmm.
would your airspeed indicator read a lot lower?
Good point. So the comment there was, if you had a high angle of attack, is that going to affect the indicated airspeed? What do you guys think? So here's our pitot tube. Let's say this right here represents our pitot tube, and it's mounted like right here on the aircraft. All right. So the comment was, if you have a high angle of attack, is that going to affect the airspeed indicator reading? So let's take a look at it. So here's our flight path right here, right? Our flight path is like this. This is not the flight path. This is the pitot tube that I'm using right here, not the flight path. So if we have a high angle of attack like this, the pitot tube is pointing up like that. You think that would affect the airspeed indicator? Yeah, it definitely does. It definitely does. It does matter. It does matter because no, again, we're not going up. The flight path of the aircraft is this way right here. So if I have a high angle of attack, this is probably beyond the critical angle of attack. But let's say we're flying like this, all right? And the pitot tube typically is parallel with the wing, the chord line of the wing. Maybe it points down just a little bit, but typically it's parallel to the chord line. We know what the chord line is, right? So this is the pitot tube right here. Yeah, that angle right there does affect how much air gets in there. So it's going to be less. So the airspeed is, if it's like this, the airspeed is probably going to be indicating lower than what our actual airspeed is. Okay, because again, that air is if we just use the pitot tube itself. If I hold this, let's say this is a pitot tube, it's just flying through the air like this. If I fly through the air like that, lots of air is going to get in through here, and it's going to show a higher indication. If I can't this a little bit at an angle and I fly through the air, not as much air is going to get through. Even though the pitot tube is flying through the air at the same speed, it's at an angle, so it's not going to capture as much yet.
Do they put little systems that'll keep it from angling up and going like?
Yeah, good point. So we actually just saw one on that. I think, well, maybe that one didn't have it. Some of them do. So what they do is they put little vanes on the pitot tube. So they'll actually have little wings on the pitot tube, and whatever attitude the aircraft is in, pitch attitude, the pitot tube is always going to be pointing into the flight path. So it's actually like a free moving pitot tube. You'll see it on commercial airliners. They've got little wings, like a little vane on there. And as the attitude of the aircraft changes, the angle of attack or whatever changes, if the flight path is like this, that pitot tube is always going to be reading into the flight path there. It could be perfect. So yeah, good comment. Yeah, good. All right. Yeah, I know you're getting confused between the climb, which in this case our flight path is this way. And again, we'll just review that. What's the flight path this here? Straight down. Aircraft, this flight path is what? It's not new. Yeah, I didn't give you a flight path. Exactly. So we don't know what the flight path is. So it's, like this one obviously is going back this way. So again, that we use that term flight path. Just remember that. That's a good concept to remember there. So, but yeah, when it's flying like this, like that, it's not, this aircraft is not climbing right here. It's just flying at a given altitude right here, but it's at a high angle of attack. Yeah.
Not really have much control over the just your rudder and
Elevator, yeah, because you get, and how, you know, in a situation like that, you've got thrust from the engine, right? Say we're doing a, just, yeah, the aircraft is just on its, on its edges. You've got plenty of thrust on that. You'd have to have lots of thrust to hold the aircraft in the air. Basically, it'd have to be enough thrust to counteract the weight of the airplane, right? On there. So, and you're saying, yeah, you wouldn't have any control to ailerons, very, very little, if anything. Most of your control is going to be through this, and not because you've got air flowing through from the flight path, because at this point there is no flight path. You're getting control of the aircraft because there is thrust on there. So, all right, let's keep moving here, guys, so we don't fall behind here. All right. Okay, I think covers all right, so let's talk, if you go to page 8-4, effective non-standard pressure and temperature. That's going to affect how the altimeter reads. So there, again, this gets back to some of the limitations of some of these gauges and things like that. If you don't have a computer calculating this for you, you do have to kind of figure this out on your own. So, so effective non-standard pressure. Let's say the aircraft is at 1,000 feet, and the outside ambient, the outside air pressure changes. Is the altimeter still going to read 1,000 feet if the outside air temperature changes? No, it's not. All right. So how do we fix that? So that's a rhetorical question. To correct for that, in the on the altimeter, the outside air temperature, again, maybe we've got a low pressure system moving in, or we're flying more commonly. You're flying from one pressure value, let's say like we've got a relatively low pressure system here, but we're flying up to northern Wisconsin, and there's higher pressure up there. When I get off there, the aircraft, the altimeter is going to be reading wrong unless I fix it. To do that, we have there's a little window right here, and there's a little knob right here. It's on every altimeter. You're going to see this right here. This adjusts for non-standard pressure, and this is in hectopascals. Let's see if they got another one here. That's yeah, these are all. This is what the type of representation you see here. So this is a type of altimeter. Again, this is pretty common. You've got the small needle right there. That again still indicates 1,000 feet. This long one, hundreds of feet, that little tiny needle right there, that's in 10,000s right there. So with this in mind, what is this altimeter saying right here? How many feet? 500 feet we got. Just make sure I got that right. Actually, I'm not sure. Let's see, 1,000. What's that? It's the opposite of the yeah. Yeah. This would be, let's see, actually, if I'm reading this right, that is 10,000 indicator right there. So that's pointing 10,000 feet, right? And this is pointing at 500. So it would be 10,500 feet is what this would be reading right here. Okay. And again, I think this is an actual diagram from the test itself. Okay. Again, this one right here is reading, again, 10,000. It's between 10 and 20,000 right here. And then this one's just under 10,000 right here. So again, that's the 10,000 feet needle right there. And this is the 1,000-foot needle. Right. Again, you'll see this, that these diagrams are on the test, and you'll have to know how to read these. So, but in any case, the whole point of going here with it was to show you this Colesman window. It's called the Colesman, or Colesman window right here. And this little knob adjusts that setting there. Let's go to the simulator where we can actually simulate this a little bit easier. So what I'm going to do here is notice how that our inches of mercury setting is changing. So I'm going to turn this. Let's say the outside, pressure is actually, and it's actually not adjusted. Let's see if I can, let me turn back off here. I'm going to unpause this so it actually shows us what's going on here. And then I'm going to turn on our setting indicator. Let's turn on our heading indicator and our altitude hold here. And we don't have to worry about. All right, so let's go here. And notice as I change this right here, how it changes the altimeter setting, or the altimeter itself. So there's two things to watch here. When I adjust this, what you're adjusting is this pressure reading right here. So we've heard, when the weather person talks about, a high pressure system is moving into the area. They're referring to this pressure right here, the outside air pressure. So what we want to do here is just change the air pressure. We want to change this altimeter setting to what the outside air pressure would be reporting at the nearest reporting station, whatever it is. So let's say below us at roughly at sea level, it's they're reporting 30.1 inches of mercury. So if I change that right here, it's going to change our altimeter right there, and it's going back down because I've got the autopilot on. So that's what's happening there. But so this allows us to actually just.
I think your horizon indicator.
Now we're going to I think we just want to do a spin here. So let's just pause here. So yeah, and again, all I'm trying to do here is just show how that altimeter works there. So again, when you're traveling from one pressure area of pressure to another, you're going to want to check your altimeter setting there. Again, what that does is it helps us identify what our real altitude that we're flying at. So let's take a look at this diagram here. They've got a really good diagram that just shows this. Let's see, here we go. All right. So let's say we depart an airport, and it's not a good one here. Let's use this one. Okay, yeah, this is a good diagram for this. So we're going from an area that has relatively high pressure right here, and it's indicating that we're at 5,000 feet right here. We go. Let's see. Make sure I'm reading this right here. Yeah. Okay. The reading here is inside the aircraft. The altimeter is showing 5,000 feet. If we go to an area that is, let's see this here. Let's see if I can find another one here. Well, let's do it by hand. I thought they had a diagram in here that actually showed this, but I don't see it anywhere. All right, so let's say our altimeter is indicating 5,000 feet, right? And the outside air temperature or air pressure, the ambient air pressure is 30 inches. If we keep flying and we stay at an indicated, it's important, the indicated altitude of 5,000 feet, and we decide we actually fly into an area of low pressure, what altitude would we be at? It's hard understanding this. So you have to think about it. So we're at 30 inches of, for our barometer reading, it's 30 inches of mercury, right? At 5,000 feet right here. And we're heading into an area over here that is a low pressure right here, okay? So high pressure going into low pressure. What is, if we stay at the altitude 5,000 feet, we're going to be higher here or lower here. This is a tough one. You're saying lower pressure, all right? So it's low pressure. So what is that going to do? Let's say we fly into this, and I'm holding the plane up, and I'm keeping it 5,000 feet above the ground. Do it this way. So 5,000 feet above the ground, and I move from an area of high pressure to an area of low pressure. What's that to our altimeter? Donnie? It's actually, I know it's confusing. Again, I'm holding it in the pole, and I'm holding it at 5,000 feet, and I'm keeping it at 5,000 feet above sea level, and I'm just moving from an area of high pressure to an area of low pressure. And the altimeter should show higher. Okay, it should say it's higher. Okay. Now, if we fly, say when we're flying, we don't have something cool as 5,000 feet. All we do is reference the what's on the indicating on the altimeter. So in that case, if we go from high to low, from a high pressure area to low pressure, we're going to have to descend to maintain the 5,000 indicated. This is tough, guys. If you really hurts my brain whenever I think about it. So really simple memory mnemonic for our memory aids is from high to low, look out below. Memorize that, because that's going to serve well when you take the test. High to low, look out below. It's high pressure to low pressure. The aircraft, to maintain the altitude, indicated altitude, now the indicated altitude, not the true altitude, the indicated altitude that's inside the altimeter and the aircraft itself, from high down below. That means that you're actually lower than what your altimeter is currently reading. And it's just the opposite if you're flying from low pressure to high pressure. Okay, if you're going from low pressure to high pressure, you're going to have to climb to maintain the same indicated altitude, not actual altitude. Okay, does that kind of make sense? And again, it hurts the brain because there's so many things happening. You've got the changes in the altimeter and stuff like that. So you have to think about the outside pressure. Just remember that as you climb, the air pressure decreases. What else changes the density of the air? We saw there's air pressure. What else changes the density of the air? What's that? Temperature. Yeah, heat. Exactly. Absolutely. So let's talk about that. So and again, there's a mnemonic or a memory aid for that as well, from hot to cold, we're down below. So let's say we're at we're at 80 degrees temperature right here, okay? And again, we're tethered to the ground at exactly 5,000 feet above sea level, and we move from an area of hot air to an area of cold air. What is our altimeter going to do? Hot air to cold air. Yep, it's going to decrease, right? Because again, you're going from area of relatively high or higher, density air to an area of lower density air. So to maintain that same density of air, we'd have to descend a little bit. So again, that's why hot air to cold air, look out below. High pressure to low pressure, look out below. Remember those two phrases there, because again, that's going to help when you take the test. Yeah, Tony.
whenever you have a
Yeah, you should always be. No, all this stuff that we're talking about right here, you don't have to worry about if you're getting constantly changing your, adjusting your Colesman window right here, your pressure, when you're adjusting for non-standard pressure, you're changing this, and you're now reading closer to true altitude, or the true, and when we say true altitude, we're talking about MSL, which stands for mean sea level, above sea level. MSL, you see the term MSL, it's talking about basically your true altitude, which you're actually at above sea level, which may be different than how many feet you are above ground. If you're in the mountainous area, and you've got mountains around you that are 10,000 feet high, you may be at 10,000 feet MSL, but your AGL, which stands for above ground level, we'll use that a lot too, may only be a few hundred feet. So in that case, it would be disastrous if you had the wrong, the wrong altimeter setting there. And that when we say the term altimeter setting, that's what we're talking about. You're changing this knob right here. You're adjusting that knob, and it's changing your altimeter setting there. Yep. Yeah, do you guys have some questions here?
That's why like that one canyon.
Columbia River Gorge. You're talking about?
I remember you saying like Valley that was higher.
Yes, in the mountains. Yeah. Yeah. It's you have to be really careful when you're out there. You really, obviously, weather is a concern, but it's a different type of flying when you're at higher altitude. The plane moves through the air a lot faster because there's less air resistance. There's not as much air molecules hitting it, so it moves through the air faster. So the aircraft turns in a much wider arc. On that, I think we had a diagram here to show that. So, okay. Let's see. So let's talk about the different types of altitude. There's the indicated altitude. Does anybody want to take a guess what the indicated altitude is?
What it says.
Yeah, what the altimeter says. When you hear the term indicated, it literally is referring to what is being indicated to you as the pilot. So that's what you read off the dial. That's indicated. All right. What about true altitude? And if you read this off the book, see if you can do it without reading off the book. Yeah.
Your actual altitude above sea level.
Yep. And let's see. Yep. So it's the vertical distance of the aircraft above sea level. Yep. So then absolute altitude is the altitude above the ground. So that would be if let's say this right here is the surface right here that we have right here is above ground. So right here, as I'm flying, I'm flying over these things. That's my altitude above these above the computer, above the joystick. I'm coming down here. I have to go over the joystick and then coming back down. That's my above ground level there. That's the altitude above ground level. And we can't read that on the altimeter, right? Can you read the AGL on the above ground level on the altimeter? If you're above this, if you're what's that?
That's check for it.
Yeah, if you have like a radar altimeter or something like that. But actually, you can actually what's your ground level if you're over the ocean. That's sea level, right?
Cool.
Yeah, that's above ground level. So if you're flying over the ocean, that is your altitude is above ground. But obviously, in this area, we're not going to be Does anybody know what the altitude that Beverly Hills Airport is roughly? Anybody know? So it's a little over 900 feet. 120 to 980 feet, I think, around this area.
Because the ocean is rising and falling with tides.
Very, very small. It's not like it's like thousands of feet. Yeah.
Is there a set like?
It would be an average, the average mean sea level, So there's a typical average that they would use on there. So it's the whole idea there is just to give us some reference, because otherwise we really don't know how high above the ground we are. So all right, let's see. All right, so vertical speed indicator. This one's a little different. So it's very similar to the altimeter in the sense that it does have the little aneroid wafers. It's got all the little mechanisms, but there's a difference here. Again, what drives this? Is it dynamic or static pressure that drives this? Static air pressure that drives this. It's the outside ambient air pressure of the aircraft. All right. So if the outside air pressure decreases, the air pressure in this cavity decreases as well, which causes this to expand or collapse. Anybody know? It's going to expand, right? So that expands. So decreasing air pressure causes this to expand. But there's a difference here between that and the altimeter. The altimeter does not have this. This is a calibrated leak right here. And what happens is, let's say you change in altitude. I go up to, let's say I climb up 500 feet per minute to 1,000 feet, okay? So I've changed to a different outside static air pressure. But because there's a calibrated leak here, this causes that needle to go back to zero again because it's leaking out, all right? Whereas in the altimeter, that's sealed off. There is no calibrated leak. And that's how we can tell our, that's how it shows the change, rate of change in altitude. Does that kind of make sense? Got it? Everybody's got it? Okay. Again, the only difference there is that calibrated leak, and because it's calibrated, it's only going to let out a certain amount of air, and it'll always equalize with the air around it, whereas the altimeter, that's sealed with the outside air. Okay. Yeah, there's another diagram with a calibrated leak there on the static port. And that's just the same vertical speed indicator there. And here's just another diagram of the airspeed indicator, again, different, mechanisms for it. But you've got two things here. You've got the ram air going into this little wafer, aneroid wafer. You've got the static air line coming into the airspeed indicator here, and then you've got the mechanism to drive the needle on the airspeed indicator. All airspeed indicators work on this same principle. Even the ones with the technically advanced aircraft, they still use the same principle. They may have a different type of sensor. Here instead of an aneroid wafer, they may have a different type of solid state sensor, but they work on these same principles here. Okay. All right. Yeah, this is just another way of showing that you got your pitot tube. Here's the airflow hitting the pitot tube, and expands that diaphragm or that aneroid wafer, which is connected right to a little gear here, which causes this needle to appear. Yeah, just another way of showing that. So another thing you're going to see on your airspeed indicator, you're going to see various V speeds. And let's see if you guys can identify these. Let me just back out of here. Well, first off, let's talk about the V speeds. So the VSO stands for the stall speed in a specified configuration, and that's going to be typically a landing configuration. All right. Let's see here. I think this is in, yeah, here we go. It's on page 8-9. So the VSO, again, notice that it's at the bottom of this white arc right here. It's VS0, and it's not O, it's actually 0. That's in, again, it's at the bottom of that white arc. And that's all for all aircraft. That's typically it's going to be like a landing configuration. You're going to have, well, what types of things will we want to use to come in for a landing? We obviously know we need to have gear, so if we've got retractable gear, we want to extend the gear, right? But what other things might we use when we come in for a landing? Flaps, yeah, we want to drop our flaps here on the aircraft to get that. So that increases our chord line. We learned about that early on. Our chord line has changed. Our angle of attack has increased. The surface area now is longer. It's actually we've got more surface area, more drag. So it changes our stall speed, and that gives us a little bit more margin. It actually lowers it quite a bit. And this on this here, it lowers it by 10 knots, which is pretty significant. Okay. So with the flaps out, we can stall the aircraft roughly at this. I mean, obviously stall speed varies, but generally speaking, when you're coming in for a landing, the stall speed is going to be right around that 35 knot mark there. That's VS0. Okay. Then there's VS1. That is that stands for VS velocity. Whenever you think of these V speeds, they're velocities. Think of them as velocities, right? So V stands for velocity, S stands for stall, and 1 is, and that stands for the in a clean configuration. We notice that that's at the bottom of the green arc. That's with the flaps retracted. That's going to be your flaps retracted speed. And you may have other, configuration speed for more advanced aircraft, larger aircraft. They may have a VS2, VS3, or whatever. Those are for various configurations of the aircraft that would change that. Okay. Let's see. FE, does anybody want to take a guess at what VFE stands for? Yep. Maximum velocity for flaps extended, right? So what that means is we don't want to go past this speed with the flaps down. Otherwise, we're going to potentially damage the aircraft. And you will see it on some aircraft, particularly on low wings. If you look at low wing aircraft, it's really easy to see when a pilot or somebody that has flown that aircraft has actually left the flaps down and flown beyond that speed. Because what you'll see like little wrinkles here in the skin. Just imagine, so if I'm coming in for a landing, obviously we're nice and slow. There's not much stress on this flap right here. But if we go through the air super fast, and say we, the airplane's only designed to fly at 120 knots, but we're flying it at 160 knots. There's a lot of lift being produced here, but there's also a lot of pressure on that flap, a lot of drag out there. And what it does is it causes the whole flap assembly to push up and create wrinkles in the skin right here on that. So if you ever see an aircraft with wrinkles in this area, you'll know that somebody overstressed the aircraft. It probably wouldn't fly fine, but there could be some damage in there. So again, the whole idea here is we don't want to have the flaps extended above this airspeed, the VFE, flap extension speed. Okay, that's VFE, flap extension. Okay. Did you have another comment?
I just think that I remember actually seeing that our instructor had like multiple sets of flaps that like broke or snapped off from people.
Yeah, it does happen. And again, it's very expensive. I mean, you don't want to fly. Now, some aircraft, I've got the twin I have, I can actually go above the white arc with limited flaps. So I can have full flaps above the white arc, but I can actually extend, like 5 degrees of flap, maybe 10 degrees on the aircraft there, and without damaging it up to a certain airspeed. I never do it because I just don't want to put the strain on the plane. But once it's in the white arc, then you can drop your flaps. You can drop full flaps on the top of the white arc. What's that? You shouldn't. Yeah. But I mean, there are situations where you may want to drop them at 100 knots. Let's say you're really close to the runway and you're going really fast. You may, if it's your one chance to get down, there's a fire or something like that, on board the aircraft, I'm going to do whatever I can. I don't care about the flaps at that point. But yeah, generally speaking, in just normal flying, you should never, ever let that happen. Never let it happen. Okay, so let's look at some other ones. We've got the green arc again. Bottom of the green arc is VS1, V stall speed 1. That's the specified configuration. Top of the green arc is VNO. Does anybody know what that is right there? Yep.
Velocity that are not supposed to exceed except in very smooth air.
Yeah. It's actually normal operating range basically in this green arc. It's the top of the normal operating range. That's what it's right there. And then the yellow arc is what's known as the smooth air penetration speed. Yeah. That's the VNE. Yeah, that's the red line speed. That's up here. The yellow arc is just a range of air speeds from here to here. And it's bordered by the VNO, the normal operating top normal operating speed, and then the VNE, which is the never exceed speed, which is the red arc right there, that red line, radial line. That's the speed we should never go past in the aircraft, because we talked about this before. When you travel above that speed, there's so much lift being produced that it's actually bending the wings up, and it actually may cause structural damage because the wings are producing a lot of lift at that rate. So, any other questions there? Yeah.
If you would breathe the glass on the most indicator, would it start this reading?
No. It's gonna read. Oh, wait a second. What do you think about that?
Because I'm looking at this one in the vertical speed. So it's looks like it's cut off, but it's maybe like the vertical radius. I know that.
Yeah, so the comment there, or the question was, if you broke the glass in the vertical speed indicator, would it affect the reading? And the answer is, it might vary slightly, but it's not going to be a lot. There's going to be some lag there, and that's because there's like a Venturi effect, sitting inside of the cabin itself. You've got air moving fast on the outside, but still air on the inside. So there's a Venturi effect. So the air pressure inside the plane is going to be typically a little bit lower than it is on the outside of the plane. So, but again, you could still break the glass in that vertical speed indicator, and it would still work, as long as you didn't break the needle or something like that. And the reason I can say that is because in the cavity of the vertical speed indicator, it's this right here, yeah. In the cavity, what is this reading? What is this pressure reading right here? Say again. What pressure is it reading? Is it reading?
Static.
It's reading static pressure. Yeah, whatever the static pressure is, either around the instrument, outside the instrument, or outside the plane. And the pressure between the inside of the plane and the outside plane isn't that much different, where it's gonna, so it still should show, relatively accurately there. Okay. All right. So typical airspeed indicator right here. Again, you've got you should be very familiar with these different colors there, what they represent. Normal operating range, again, is the green arc. The flat operating range is the white arc. Yellow is turbulent air penetration speed, and then the red line is your never exceed speed. Those you should just know. Okay. There are a lot of other V speeds here too. Let's see. Yeah, they call it the caution range. I call it the yellow arc. They say in the book is caution range, but again, it's the turbulent air penetration speed, also known as so. Okay, that's at 8.9. Let's go here. Design maneuvering speed. This is a really hard one. So I'm going to try to do my best to explain it, but it's not something you're going to find on the airspeed indicator itself. Okay. So let's talk about this. The design maneuvering speed is the maximum speed that you can, or the airspeed that you can pull back on the control yoke without damaging the aircraft, without stressing it. Okay. So if your maneuvering speed is, let's say it's 100 knots, you should be able to pull back on the control yoke, and the aircraft is going to stall before it does any damage to the aircraft. Okay. So again, if your maneuvering speed is 100 knots, okay, and you're flying at 100 knots, and you pull back on that control yoke, the aircraft is going to stall before it gets in, it damages it. Above that airspeed, if your maneuvering speed is 100 knots, and you're trailing at 120 knots, you pull back on the control yoke, there's a good chance that you're going to overstress the aircraft and either, break a wing or a spar or something like that. Okay. So in turbulent air, we want to be flying at the design maneuvering speed, or the actual maneuvering speed for that aircraft. And keep in mind that the maneuvering speed for an aircraft changes based on the weight of the aircraft, density of the air and things like that. Why is that? Okay, so let's get into that because this is an important concept to understand. So let me throw out a question for you and think about it before you answer, okay? So the design maneuvering speed for this aircraft is 100 knots. And I'm flying let's say that we can load this up. The maximum weight of this aircraft is 1,000 pounds, okay? And we've got it loaded up with 1,000 pounds. It's now at 1,000 pounds. If I am at, let's say I'm flying along 100 knots and we're at 1,000 pounds, I pull back on the control yoke. We know that at that airspeed, the maneuvering speed at 100 knots is going to, the aircraft is going to stall before it breaks anything. Now, what if I take 500 pounds, or like, let's say 800 pounds off this, and we're now at 200 pounds of weight. We've got a little light aircraft, and we're flying along at 100 knots, and we pull back abruptly. Can we still, would we exceed the maneuvering speed? Okay, well, the maneuvering speed has changed now. Okay, this is the key part here. So let's look at it. It all has to do with angle of attack. So let's say I'm traveling, the aircraft weighs, we're at 1,000 feet, the aircraft weighs 1,000 pounds, and I take weight out of the aircraft. To maintain our altitude at 1,000 feet, what do I need to do with my angle of attack? So we just, what did I say? We actually added weight or took off weight? Took off weight. Yeah, decrease the angle of attack, right? Because we don't need as much lift anymore, okay? So 1,000 pounds, we need a higher angle of attack because we need more lift to maintain that altitude. But if we just drop, 500 pounds off that, we don't need that much angle of attack anymore, so we can drop the angle of attack down. Now remember critical angle of attack? That was about roughly 16 to 20 degrees, somewhere around there, okay? That's at the point where the aircraft, it stalls. When you're flying with a lighter aircraft, your maneuvering speed is actually going to be higher. Okay, and here's why. When you pull back on that yoke and you're flying at a higher airspeed, let's say you're producing lots of lift, you're not going to hit that critical angle of attack in time enough to prevent it from damaging the structure of the wings. Okay, that's why the maneuvering speed is going to change based on weight of the aircraft and things like that. You're going to have the angle of attack is changing. So design maneuvering speed, I guess it's a tough concept to understand, but the design maneuvering speed again varies by how much weight you have in the aircraft. That's primarily what changes it. Okay, so if you have a heavy aircraft, it's again you have a higher angle of attack. Like this, we have a higher angle of attack right there. And if I pull back suddenly, we're going to hit that stall angle of attack really quick, and the plane is going to stall before it damages it. If you have a very low angle of attack, we're a light aircraft that are flying through the air, we've got all this extra angle of attack now. We've got lots of room to pull back on the control yoke and cause stress in the wings and stuff like that, which is going to change it. So design or the maneuvering speed of an aircraft does change with weight. You'll see that on the test, guaranteed. Okay, let's see here. Okay, so let's talk about a couple other things. Landing gear operating speed. This is on page 8-10. Landing gear operating speed has to do with the speed at which you can operate, the maximum speed at which you can operate the landing gear. So if in my plane it's 150 miles an hour, and I usually try to get underneath that airspeed to deploy, because it's hard on the structure of the aircraft and also the gear when you drop it. So if you are below that speed, it will be less stress in compliance. Again, VLO stands for landing gear operating speed. Again, that's a maximum speed for landing gear. Landing gear extension, extended speed, that's the maximum speed that you can have the gear extended, which sounds like it's the same thing as landing gear operating speed. But there is a difference there. So let's read through it. So the VLO, the maximum, that's the maximum speed for extending or retracting the landing gear. The VLE is the maximum speed at which the aircraft can be safely flown with the landing gear extended. There's a difference there. One, it's just the VLO is operating the landing gear. I do want to operate it at above that speed. VLE is the landing gear can fly safely at that landing gear extended, and that could be if you're ferrying an aircraft, or maybe you had some problems with the landing gear and you've got it stuck down. Well, there's a speed that you can fly at that safely that won't cause damage to the aircraft. All right, so the next two are super important. So there's best angle of climb speed, and then there's best rate of climb speed. And this is going to be easier to draw out on here. Let's see if I can get a whiteboard on here. There we go. So, and they do have a diagram on here, but let's just draw. This is our surface right here. Here's our plane right here. And the best angle of climb is, think of angle of climb as the best angle that the plane can climb. So basically, it's the most altitude for a given distance, right? All right. It's the best angle of climb. It's the best altitude gain for a distance. The best rate of climb is the fastest path to altitude for the same given amount of time. So let me see if I can do this better here. There's a way to draw this that yeah, so let's do this here. So right, so our best angle right here, this is our best angle of climb right here. So this is, again, this is our plane right here. And let's say, let's draw it here. And let's say this is just 2 miles right here, 2 miles. And then our best rate of climb, it's going to be a lot higher. Let's see. So this is right here. It's the best rate of climb. Let's say the 2 miles here took us 10 minutes to climb, or that would make sense. So let's just say it maybe took us 2 minutes. 2 minutes here. Yeah, that's not. Let's back up about that here. So good. So the best rate of climb is let's see here, is actually our best altitude gain for a given period of time. So if this took us 2 minutes, in the same 2 minutes here, instead of climbing, let's say like this was 1,000 feet right here for best angle of climb. This gets us 1,000 feet. For 2 minutes on our best rate of climb may get us to 2,000 feet. Okay. Right. That's an extreme there, but let's just say for, again, 2 minutes for best angle of climb. Again, in the case, it's going to cover less distance there, but we're not going to gain as much altitude. It's just a short distance. Whereas best rate of climb, we're going to climb a lot faster for a given period of time. So if this is 2 minutes here, we may climb a lot higher, but we're also going to cover a lot more ground. This right here is like 2 miles. This may be 7, 8 miles here, this distance from here to here. So one is based on distance, that's the best angle of climb. And then the other one is based on time. You're going to get your best rate of climb based on your, I'm trying to say here the distance traveled or the time used there. So 2 minutes for best rates. This is V. VY. And notice that VY has only one angle, VX, that's your best angle of climb. It has lots of angles in it, X. It's got lots of angles there. That's the way to remember them. And you may come up with other memory aids there for it. That's what I use. So your velocity, best angle of climb. We use these all the time in performance calculations. So I get familiar with those two. And actually all of these speeds, I get comfortable with using all of those. Let's turn that off. And that talks about airspeed there. Let's see where we're at. Let's go over. Yeah, there is on that 8-10. There's a single engine best rate of climb as well. That's for a multi-engine aircraft. You probably won't see that on the test because it's for single engine aircraft, but suffice it to say that VYSE stands for single engine best rate of climb. And then conversely, VXSE would be best angle with a single engine. Most of the training aircraft you're going to fly are all single engines, so it's not going to be applicable for most people training. So the VMC, that's the minimum control speed for a multi-engine aircraft. Again, we really don't have to know that for your private pilot test, but again, that's only going to be seen with multi-aircraft or multi-engine aircraft. All right, so a couple of things I do want to talk about is blockages in the pitot-static system and how they affect the pitot-static ports there. We can get into a lot of details. Definitely read the book on this, and read through this. They've got some text in there that kind of describes it probably better than I'm going to explain it here. But let's just read through this blockage of the pitot-static system. Okay, a block pitot tube affects the accuracy of the airspeed indicator, right? That makes sense, right? The pitot tube drives. Well, does it pitot tube drive any other instruments? No, doesn't drive any other instruments. The pitot tube only drives the airspeed indicators. Yep. Okay. It's the static port that drives all three of those instruments, the pitot-static instruments. So blocked pitot tube affects the accuracy of the ASI, which stands for airspeed indicator. But a blockage of the static port not only affects the airspeed indicator, it also causes errors in the altimeter and a vertical speed indicator. So let's talk about first about a blocked pitot-static system. So if the pitot tube becomes blocked and its associated drain hole remains clear, ram air is no longer able to enter the pitot system. So let's see, let's go back up to here. So if this right here, if there's a blockage right here, and the drain hole is open, we essentially have an altimeter. That's what it is, because we don't have any, ram air getting pushed in there. So let's take a look here to make sure I'm right here. Okay, that's through. Yeah, under these circumstances, the SIA reading decreases to 0 because the that's just static air pressure. Let's see, is that right? Yeah, okay, so they're saying here, under these circumstances, the ASI airspeed indicator reading decreases to 0 because the ASI senses no difference in the ram air and the static pressure. So yeah, so it actually just would read 0. If both the pitot tube opening and the drain hole should become clogged simultaneously, then the pressure in the pitot tube is trapped. No change is noted on the airspeed indication should the airspeed increase or decrease. So that's when this is completely blocked off here. Let's see. Again, read through these different scenarios. Again, you're probably going to see this on the test. They'll talk about blockages, what's going to happen to the airspeed indicator on there. So, and knowing which things are doing what, which holes on the like the pitot tube and the static ports, what they're doing helps with this. Right. let's go through here. Here's a good picture of a static port right here. That little metal plate, that's what heats out there. Okay. Let's see here. Again, there's another picture of a pitot tube right there. So that's a very common one for Cessna micro aircraft there.
One on that line is fed.
What's that?
The Peter 2 on that aircraft right there is actually fed.
It's a, I'm sorry?
On that aircraft, Peter 2 is like fed.
Oh, fin, it does have a fin on them, okay. All right,
I was looking at that.
interesting. But a block static system is going to act differently as well. A block static system is going to change, obviously, as the air is going to get trapped inside the, let's see if I can go through here. Yeah, a block static system right here is going to affect, obviously, all these instruments that have the blue line going to them. So every one of them is going to be affected. It's going to freeze the altimeter. You'll have just a straight constant indication of the VSI. And then obviously your airspeed indicator is going to have inaccurate readings there. That's, again, if you have your static right there. And I tell you what, guys, we're going to call it a day after this. So that was around 8:12. We'll finish up that chapter next week. I was thinking we'd do the simulator next week, but I think we're going to finish up. I want to get through this stuff. I want to get to the point where we're kind of ahead of the game a little bit. And what we'll do is we'll schedule the sim for another day when we've got some time, and we'll just do simming all day for that session there. So again, next week we'll cover chapters 8 and 9. We might get into chapter 10 next week. So, which is weight and balance. Pretty easy.
Thank you.
Yeah, thank you.
Message.